Okay, so in chapter 23, what we're talking about is inferences about means. We learned a lot about proportions, and what's nice is a lot of the same rules are going to apply. And the man who found this, his name was William Gossett, and let's see, he worked for a Guinness Brewery in Dublin, Ireland, and his job was to make sure that the stout was of high enough quality before it was sent out. And so while he was doing this, he was using traditional statistics, looking at proportions in the normal model. And when he was doing this, he realized that his process wasn't making the type 1 errors 5% of the time like he had predicted, but it was actually 15% of the time. And so he was upset about this or baffled by this because he couldn't figure out what was going on. And so he ended up taking time off of work and went back to school to study statistics. And when he was doing that, he determined what was wrong, and he learned that for means you have to do something called a degree of freedom, degrees of freedom. And what's interesting about this little side note is that he wanted to publish the paper, but Guinness didn't want him to publish the paper because they were worried he was going to publish all their secrets on how they made their beer. And so he had to publish the paper under student X or student. And so now when we talk about a mean model, it's actually called the student's T model. And it was never named after him. Okay. And so if you look here, the blue right there is what a normal curve looks like. And here's the mean. And if you go 3 standard deviations out to the left or 3 standard deviations out to the right, that's where it about ends. And that's what a normal model does. But what he was finding with the mean is with 1 degree of freedom, it was a fatter tail and it didn't go as high. Okay. So then let's look and see what happens with 2 degrees of freedom. Again, the blue is the normal. The green is what 1 degree of freedom is, and then the red is what 2 degrees of freedom are. Okay, so if you notice, I'm a little closer to the normal model now with 2 degrees. And then the same thing's happening here with 3 degrees. I'm getting closer and closer to the normal model, so that's 3 degrees of freedom. There's 5. There's 10. It's getting closer and closer. And finally, 30, when you get to about 30 or higher, you're pretty much at a normal model. So again, Gossett had discovered that degrees of freedom is kind of what helped make the mean models more normal. And so the model that he discovered was the student's T model, which is a family of distributions that depend on degrees of freedom. Now, when we're working with means, the expression that represents the degrees of freedom is n minus 1. And remember, n is your sample size. So whatever you have is if you have 10 people that you sample, then it would be the degrees of freedom is 9. And so this is the degrees of freedom for means. Okay? All right, so there's some things that you should remember. And the smaller the sample, do you remember what happened to the tails? Yeah, the smaller the samples, the fatter the tails. Okay. Another thing that you should remember and recognize is that as the degrees of freedom, the DF, increases, did you notice that the center and the shape didn't really change? The center and shape stayed the same. But what happened was the spread got smaller. And yes, the shape did change a little bit and got skinnier, but that's because the spread was coming in. So it didn't go from unimodal to bimodal, okay? So it stayed the same that way. And then one other thing is, again, just it makes kind of sense, is that if you increasing the degrees of freedom, it's the same thing as increasing sample size. Because the degrees of freedom is taken from the sample size. Okay? All right, so what is nice about this, yes, it's another model, but it's a lot of the same rules that we've already had to deal with. You already know how to check if things are random. You already know that 10% is less than 10% of population. You know that. Independent, yeah, a lot of times we check if things are independent. And we just have to check to make sure that one mean doesn't affect another mean. So that's what the independent does. The new one that we have to get used to is we have to get used to that it's a nearly normal condition. Okay? And so what you have to look for here is you have to look if it's unimodel. So there's one hump and that it's symmetric. Those are the things you got to kind of check. And there's several ways to do that. You can look at the histogram or a box plot. Now, if you remember when we were looking at those different degree pictures, the higher the sample or the higher the degree of freedom, the more it looked normal. So kind of the rules kind of look the same. If you have a small sample of less than 15 or so, it's not exactly 15, but about 15, it should be pretty close. It should be pretty close to a normal model, and it should look pretty close to a normal model. If there's outliers or skewness, don't use this model. Don't use this method. Okay? So if you have a relatively small sample size, which means a relatively small degrees of freedom, you should not use it if you see extreme outliers or skewness. And we'll talk more about when is it extreme or when is it really skew. Okay? All right, so the medium size, which is about between 15 and 40, they work well. So the T models, which is what we're dealing with, work well as long as unimodel. They are unimodel and not skewed. So and symmetric. Okay? So again, if you see anything really drastic, really skewed, or really definitely a bimodal, it won't work for this. Okay? The last thing, a large sample. When you get above 40, and again, that's an about number. When you get above there, the T model is safe to use. And it's safe even if there is skewness. Okay? What happens here, though, is if it's skew, you can run this model. But if there's outliers, we're going to have to run it twice. We're going to have to run with and then run again without the outliers and see what happens. Because a lot of times outliers are really what tells us or gives us information about our data. Okay? All right, so down here, the margin of error, it may look a little different, but it's pretty much the same formula we have, except our critical point now is not Z, but it's T to the n minus 1, which means it's the critical point for your degrees of freedom, because that's what n minus 1 is. Okay? So this is the critical point for T models. And again, what's nice is you already know how to find it. It's the exact same process as what we were doing with proportions. Okay? Over here, remember, SE is your standard error. And so this is the standard error for the population, which is the standard deviation for the sample. And we've actually worked with this a little bit. Okay? All right, so now when you calculate your critical point for T, you're going to use the inverse T. And so we do it the exact same way as before, where if you remember, if I wanted something that was 92% confidence, we kind of draw our picture, and 92% is here. So that leaves 8% for both of these, so this is 0.04. So the only difference is here now we have to use the inverse T for T model, okay? And so for this one, it would be the inverse T of 0.04. And then the second thing that goes here is the degrees of freedom. And so let's say our degree of freedom is 12. And so the calculator key, again, go second distribution, go down to number 4. Oops, passed it. So it was 0.04, and our degree of freedom, I said, was 12. And so then that would give us our critical value point of negative 1.91. And remember, we just have been dropping the negative because we don't really want the negative, okay? All right, and so this is the exact same process as we were doing before, but now it's just the inverse t, and you have to use your degrees of freedom, okay? And so remember, that was the little formula some of you were remembering. It was 1 minus the confidence. So 1 minus 0.92, and then divide by 2. And that would give you what's there. Okay? Okay, so all we're going to do now is we're just going to do some problems, okay, where we're going to plug them in. And so for number 1, I might try and squeeze this on here. If you have space, you can. Otherwise, you can put it down below. But so I want a 92% confidence, which we kind of already figured out. So it's the inverse t. 1 minus 0.92 is 0.08, and then I'm going to divide that by 2. Okay? And then same thing here, inverse t. And why don't you actually pause this, try it on your own, and then come back. Okay, so there's the answers. Remember, if you get a negative, you're just going to turn it into a positive. Okay, so now, when we get to 3, 4, and 5, we have to calculate the p-value, okay? And so essentially what we're going to do is we are going to use the TCDF function, okay? And so when you do the TCDF function, it's the lower, upper, and then your degrees of freedom, okay? So I want to be greater than 1.45, so that means that's my lowest point. So 1.45, I'm going to pick some big number. I'm going to say about 100, because that's pretty big. And then my degrees of freedom is 8. Okay? So let's clear this out. Go second distribution, TCDF. And so my lower was 1.45. My upper was 100. And my degrees of freedom was 8. And so I get 0.0926. And so that would be my p-value for that, okay? All right, if I look at this for the next one, again, it's the TCDF. This time I want to be less than that. So my lower function is everything to the left of that, so maybe negative 100. The highest value I want is this, the 2.31, so negative 2.31, and my 12 degrees of freedom. So again, you just go to the function, TCDF, negative 100. Oops, I said 1,000. That's okay. Negative 2.31. And negative 100 might be overkill, but it doesn't hurt to have a bigger number. Okay, and we hit enter. And so it's 0.0197. So that's a lower p-value. Okay. And then the last one, it says I want to be less than this, okay? So I'm going to draw the picture for this one so you can see, because it's saying the absolute value. So it's saying that essentially, here's the mean, 2.14 is about here, and you want to be less than that, so you're going to be to the left. But if you remember absolute value, when you are solving an absolute value equation, it also is the opposite of that, so negative 2.14. And so I'm looking for this range here, okay? Because it said less than, I want to be to the left of 2.14, forgot the 1, and to the right of negative 2.14. So I would do the TCDF of negative 2.14. The upper region is 2.14, and the degree of freedom is 19. Now, if you had a question that said the absolute value of t is greater than, let's say, 1.7, what would happen here is 1.7 is right about here, and I'd shade to the right. but then I'd have to go to the left of negative 1.7. So for this one, what you would do is you could do one of them and then multiply it by 2, or you can find both of these by doing TCDF functions and then just adding them up, okay? All right, so what I'm going to do now is pause for a second to get the textbook. If you want to open up your textbook, we're going to look at numbers 11 and 13 together. We are almost done, though. You guys are doing well. When we look at number 11, it says the researchers described in Axel 9 took the body temperature of randomly selected adults. Below is the information they collected. Okay, so the first question is asking you, is it appropriate? Can we meet the conditions? Well, let's look at these conditions. Yes, it said it was random. Is it less than 10% of the population? Well, 52 is definitely less than 10% of the population. The next thing is independent. Yes, I believe that adult body temperature does not depend on somebody else's body temperature unless they all were in a hot room, but I still don't think that would make a difference. And then the next thing we need to do is look, is it nearly normal condition? And if you notice this, yeah, this is pretty normal. And there's nothing, this might be an outlier, but it's really not that big of a deal. With 52, I think we're going to be good. Okay, so what we have to do is find a 98% confidence interval, okay? And so confidence intervals, remember, we have to have all this information, so let's write down what we need. We need to know the mean. The mean is 98.285. We need to know the standard deviation, which is 0.6824. And the other thing we need to know is n, which is 52. From that information, we should be able to answer everything, okay? All right, so the first thing we need to do is let's figure out our degrees of freedom. Well, if our sample size is 52, the degrees of freedom is 52 minus 1, which is 51, okay? The next thing we need to do is figure out 98%. I'm just going to write that down so I remember. So now we go back to our margin of error formula, which is right here. So it's the exact same idea as what we were doing before, but now we just have some different numbers. So it's t n minus 1 times the standard deviation over the square root of n, okay? And so right now I can go ahead and fill in this. The standard deviation is 0.6824 over the square root of n, and n is 52. What I need to find is this t star, okay? So that's when I'm going to have to do my inverse t. And remember, if I have 98%, that leaves 1% over here. So it's going to be 0.01. And then the second number here is your degrees of freedom. And our degrees of freedom was 51, okay? So let's plug this in. Inverse t, 0.01 and 51. And so we get negative 2.402. So I'm going to say that's positive. Remember, we want the positives. And so to make it the most accurate as possible, I'm actually just going to change the sign of this. So I'm going to do negative answer, because that's just going to change the sign. And then I'm going to times by this stuff, 0.6824 divided by the square root of 52. And so I know my margin of error, if I can get both here, my margin of error is 0.227. And so now to find the confidence interval, remember I'm going to add that and subtract that from our mean, which was 98.285. So 98.285 plus 0.227, which gives me 98.512. And then I'm just going to go up and change that to a minus 98.058. And so that's our confidence interval, okay? All right, if we look at the textbook, the next question it asks, explain the meaning of that interval. Well, that's when we say that we are 98% confident that the true mean or the true average adult body temperature is between here and here, okay? Okay, so here's the statement written out. We are 98% confident that the true average adult's body temperature is between 98.058 and 98.52. When you look at part D here, it says explain what 98% confidence means in this context, and I already have it written out for you. It just means that in 98% of all such random samples, they will give us an interval that contains the true average of adult body temperatures. So it's saying it'll happen all the time. That's 98% of the time, okay? All right, and then the last question is saying 98.6 is commonly assumed to be normal. Does this data suggest it? Well, when you look at our confidence interval, 98.6 isn't even in there. So I would say no, it doesn't suggest that that's accurate. Okay, all right, let's look at 13. Okay, so it's telling you to look at this again. And the first question is asking you, well, what if we changed it to 90% confidence? Well, remember, this is what 98% looks like right here, right? And this is what 90% looks like. It's not as wide. So if it's not as wide, then it has a smaller margin of error, so we would be less confident about that, okay? The second question asks, what are the advantages and disadvantages? Well, the advantages are that it's a greater chance of having the actual mean, the true mean, greater chance of having the true mean. And the disadvantage, whether or not it is a disadvantage, but the disadvantage, let's see if I can spell, nope. The disadvantage is that it's a wider interval, okay? I would say another disadvantage is that sometimes it's harder to get that. You sometimes have to have a, larger sample size. Okay, and then the last part, or C, if we conducted further research, assuming using a sample of 500 adults, how could you expect it to be? Well, the more people you have in the sample, remember, the more accurate it is. And that also means that it's going to become narrower. Remember, the more people you have, the sample gets closer and closer together, okay? And so it would just be a smaller interval, okay? All right, and then the last question is asking you to find what you would need for 98% confident. So I already have it worked out, so I'm going to kind of just show this. So we have a margin of error this time of 0.1 with 98% confidence. So I kind of just jumped in and wrote it out, plugged it in, but remember it's T times the standard deviation, not S. Standard deviation over square root of n. And here I rounded differently than what I did on the front page when we did the notes, but either one, it's going to always give you a little bit of a different answer depending on what you chose, but if I see your process, you will be good. And then so I solved that equation, and so it should be about 267. I believe if we would have stuck with the 2.402, it would have been a little different, okay? But that's it. So what you need to do now is I have some questions next to this video. I need you to answer those questions, and they're just calculation questions, seeing how you do using the calculator. And when you type in your email address, it will automatically send you an email saying how you did on those answers, okay? And then the next thing I need you to do is I need you to make comments, at least one comment or question in the blog. And if you would like to comment on somebody else, I would love that. I would love for you guys to start helping each other out and talking about things on the blog there. All right, I hope that you have enjoyed your spring break. And sorry this video took too long, but that's the only thing you had to do for me this spring break. So I will see you Monday.